on September 14, 2015, at exactly 9:50 in the morning, Universal Time, a ripple passed right through your bedroom.
Completely invisibly, too.
Yeah, invisibly. It didn't matter if you were awake or asleep or, just sitting in traffic. This wave washed over you,
Right.
and it stretched the physical space beneath your bed by this impossibly small amount. I mean, less than the width of a single proton.
Which is just mind-bogglingly tiny.
Totally. And then, like, a fraction of a millisecond later, it compressed the wall beside you by the exact same microscopic margin.
And nobody felt it.
Right. Nobody on Earth felt it. But two massive hypersensitive machines in the U.S., one in the Louisiana swamp and the other out in the Washington desert, they actually caught it.
Yeah, they measured that tiny little wobble.
Which is wild because that invisible ripple had been traveling through the void of space for, what, 1.3 billion years?
Yep, 1.3 billion.
And it was carrying this secret, born from a violent collision of two black holes in a distant corner of the universe.
And when that wave finally hit us, it confirmed something that had been theorized exactly 1 century earlier.
Exactly. Welcome to the Deep Dive. Today, we are taking you on a massive journey.
Oh, yeah, we've got a huge stack of sources today.
We really do. We've got historical accounts, transcripts from science documentaries, Wikipedia deep dives, and even some wild virtual reality simulation notes.
It's a lot to get through.
It is. But our mission today is to distill all of this down to explain special and general relativity. We're going to build Einstein's universe from the ground up.
And we're tailoring this specifically for you. So, like, imagine you're a high school physics student or, honestly, just someone who wants to finally understand how the universe actually works beneath the hood.
Right, because we aren't going to bog you down with terrifying math.
No math tests at the end of this.
Definitely not. You won't need to memorize any complex equations. We are going to focus purely on the mind-bending thought experiments, the human history, and, well, the ultimate rule book of the cosmos.
We really want to explain the why and the how, not just the what.
Exactly. So where do we even start with this?
Well, to really understand why Einstein's ideas were such a profound revolution, you first have to understand the absolute crisis that shattered physics in the late 19th century.
Okay, the crisis.
Yeah, because without understanding the crisis, the revolution makes absolutely no sense. I mean, if you were a physicist back then, you thought you had the universe pretty much figured out.
I'm trying to picture what physicists actually believed before Einstein came along. Like, if I'm a scientist in, say, 1890, what is my fundamental assumption about how the world works?
Right. So in the 1890s, your understanding of physics was resting incredibly comfortably on two magnificent, seemingly unshakable pillars.
Okay, two pillars. What's the first one?
The first pillar was Isaac Newton's classical mechanics. He formulated this way back in the 17th century.
Right, the apple falling from the tree guy.
Exactly. This was the mathematics of everyday motion. It was beautifully intuitive. I mean, it predicted falling apples, the parabolic trajectories of fired cannonballs, the sweeping orbits of the planets.
The stunning accuracy. Right.
Oh, reliable, stunning accuracy. You could calculate exactly where a planet would be 100 years in the future just using Newton's math.
So it was pure common sense. It's the physics you and I can see and feel every single day. Like, if I push a cart, it rolls. If I drop a rock, it falls.
Precisely. That's pillar one.
Okay, and pillar two?
Pillar two was a bit newer, but just as powerful. It was James Clerk Maxwell's theory of electromagnetism, published in the mid-19th century.
Maxwell's equations.
Yeah. Maxwell managed to unify electricity, magnetism, and light into 4 elegant equations. He realized they were all the same phenomenon.
Which is a huge deal on its own.
It was massive. And his equations predicted something highly specific. They showed that light is an electromagnetic wave, and it travels at a fixed, constant speed.
Right, the speed of light.
Specifically, 299,792,458 meters per second in a vacuum.
Enormous, but precise. It's a finite speed limit.
Exactly. But here's where the nightmare begins for our 1890s physicist.
Uh-oh.
These two magnificent pillars, Newton's mechanics and Maxwell's electromagnetism, they contradicted each other in a way that seemed totally irreconcilable.
Wait, how so?
They simply could not both be right.
Okay, let's use the classic train analogy from our sources to really visualize this clash for you.
That's a great way to show it.
So imagine you are standing on a flatbed train car that is moving smoothly forward at, let's say, 100 kilometers per hour.
Okay, got it.
You have a baseball in your hand, and you throw it forward toward the front of the train at 50 kilometers per hour.
Right.
To you, standing on the train, That ball is moving away from you at 50 kilometers per
But
hour.
you're the one throwing it.
Exactly.
Eh,
But imagine your friend is standing on the station platform watching you go by. To them, those speeds add up.
Yeah, they see the train moving at 100 plus the ball moving at 50.
So they see the ball moving at 150 kilometers per hour. That is Newtonian mechanics.
It just makes intuitive sense. Velocities add together based on your perspective.
Right. There's exactly how the universe works in Newton's mind.
But Maxwell's equations said something entirely different about light.
Okay, here we go.
Maxwell's math stated that the speed of light is always that exact same number, about 300 million meters per second, regardless of how the source of the light or the observer is moving.
Okay, I have to stop you there and push back on this because this is where my brain starts to hurt.
It hurts everyone's brain at first.
Let's go back to the train. Let's say this is a futuristic train moving at 200,000 kilometers per second. Super fast.
Very fast train.
I am standing on the roof, pointing forward, and I turn on a powerful flashlight.
Okay.
According to Newton's common sense, my friend on the platform should see that beam of light traveling at the normal speed of light plus the speed of my super-fast train, right?
That's what Newton would say, yes.
But you're telling me Maxwell says no.
Maxwell's math firmly says no. The light does not speed up. Your friend on the platform measures that light beam traveling at exactly 299,792,458 meters per second.
No addition at all.
No addition, no exception.
But wait, what if I'm in a spaceship going 99% the speed of light and I turn on my headlights?
Okay, taking it to the extreme.
Does the light barely inch away from the front of my ship from my perspective? Because if the light zips away from me at full speed from my perspective inside the ship, then the guy watching from Earth would have to see that light going 199% the speed of light.
Right.
It has to be one or the other. That makes absolutely no sense.
Well, you have just articulated the exact paradox that was keeping physicists awake at night in the 1890s.
Really? Just that simple contradiction.
Yes. How can the speed of light be constant for everyone, everywhere, regardless of how fast they're moving?
It seems impossible.
The standard explanation they came up with to save both Newton and Maxwell was something called the luminiferous ether.
Oh, the ether. Because they couldn't imagine a wave waving through absolutely nothing, right?
Exactly. I mean, if you have a sound wave, it's just air molecules bumping into each other.
Right. And if you have an ocean wave, it's water moving.
Exactly. The scientific community reasoned that if light is a wave, there must be a physical medium carrying it. So they hypothesized the ether.
What exactly was it supposed to be?
An invisible, massless, perfectly rigid fabric that filled the entire vacuum of the universe.
That's convenient.
Very convenient. The idea was that the constant speed of light from Maxwell's equations was simply its speed relative to the stationary ether.
Oh, I see.
If you accept that the ether is just sitting there in the background, the contradiction seems to vanish. Light travels at light speed through the ether, and the Earth is just moving through that ether.
But that means if the ether exists, you have to be able to detect it.
Right. Which brings us to the famous Michelson-Morley experiment of 1887.
Yes. This is one of my favorite stories because the lengths they went to are just wild.
They were incredibly thorough.
To detect this invisible ether, Albert Michelson and Edward Morley went down into a basement laboratory in Cleveland, Ohio.
They needed a setup completely isolated from any vibrations.
Right, like even a horse-drawn carriage rumbling down the street outside would ruin the measurements.
So what did they do? They took a massive, heavy sandstone slab and floated it on a circular pool of liquid mercury.
Liquid mercury, just a giant pool of it.
Yeah, the mercury bath allowed this heavy slab to rotate smoothly with near zero friction, and it acted as a perfect shock absorber.
That is brilliant. And so on top of this floating slab, they built an interferometer.
Which is a fantastic piece of equipment.
Now, if you're wondering what an interferometer is, it's actually a brilliant device. They took a single beam of light and shined it through a half-silvered mirror.
Basically a two-way mirror.
Right. This split the single light beam into two separate beams, traveling perfectly perpendicular to each other, kind of like an L shape.
Okay, picture the L.
These two beams traveled down long arms, hit regular mirrors, bounced back to the center, and recombined into one beam that hit a detector.
And the logic here was impeccable.
How so?
Well, the Earth is plowing through space as it orbits the sun at roughly 30 kilometers per second. So the Earth should be creating a constant ether wind as it pushes through this invisible fabric.
Ah, like feeling the wind in your face when you ride a bike.
Exactly. By splitting the light into two perpendicular beams, one beam should be swimming upstream and downstream against the ether wind, while the other is swimming cross-stream.
Right. If you swim up a river against the current and then back down, it takes longer than if you swim perfectly across the river and back, even if the physical distances are exactly the same.
Because the current slows you down more than it helps you?
Precisely. So
Yeah.
when those two light beams recombined at the detector, they shouldn't arrive at the exact same microscopic instant.
They'd be slightly out of sync.
The waves of light would be slightly out of phase. The peaks and troughs of the light waves wouldn't line up anymore, creating a visual interference pattern.
Like a specific pattern of light and dark bands.
And by slowly rotating that giant sandstone slab in the pool of mercury, they should have seen that interference pattern physically shifting as the arms of the machine changed their orientation relative to the ether wind.
But they rotated the slab
It's
and
nothing.
a complete null result.
The light beams returned at the exact same time, every single time, no matter which way the slab was turned, no matter what time of year they ran the experiment.
The Earth wasn't dragging through any ether wind.
The ether just didn't exist.
Albert Michelson was devastated. He genuinely thought his experiment was a massive failure, just a complete waste of time and money.
Which is so sad, because in reality, it was the most successful failed experiment in the history of science.
Oh, absolutely. Because it proved that light doesn't need a medium. It proved the speed of light really was a universal constant.
Which meant the crisis was worse than ever.
Yes, the universe was broken. But it paved the way for someone to look at reality without the crutch of the ether.
And that brings us to a young Albert Einstein.
Enter Einstein.
I really want to highlight the historical context our sources provide here because they shatter a really pervasive, annoying myth.
Oh, the math myth.
Yes, we always hear that classic trivia fact. Even Einstein failed math in school.
I hate that one.
It is totally false. It's a myth born from a 1930s Ripley's Believe It or Not column.
People just love the idea that a genius struggled with basic stuff.
Right, but the truth is, by the time he was 12 years old, the kid was voluntarily teaching himself differential calculus and devising his own original geometric proofs for the Pythagorean theorem.
Yeah, he was a prodigy. But what's deeply insightful here isn't his raw calculating power, but what actually sparked his curiosity.
It wasn't formal schooling, right?
No. In fact, he despised the German educational system for its rigid, authoritarian memorization tactics. His defining moment actually came from a pocket compass. Yeah. When he was 4 or 5 years old, he was sick in bed, and his father gave him a compass to play with. Einstein watched that little magnetic needle tremble and settle, always pointing north.
Being moved by a completely invisible force.
Exactly. No strings, no hands pushing it, nothing physical touching it.
He later described that moment as experiencing a deep shudder of wonder.
Which is a beautiful way to phrase it.
It was his realization that something deeply hidden had to be operating behind the curtain of everyday things.
And that profound sense of wonder led to a thought experiment when he was just 16 years old.
Just a teenager.
A thought experiment that would eventually unmake the universe.
The 16-year-old Einstein is walking around, and he asks himself, what would happen if I ran alongside a beam of light at the exact same speed?
It sounds like an innocent, almost childlike question.
But it is conceptually devastating.
It really is. I mean, if you could somehow catch up to a beam of light, you would theoretically see it as a frozen electromagnetic wave.
Just a static, motionless oscillation hovering in empty space right next to your face.
Kind of like looking out your car window on the highway at a car driving the exact same speed as you in the next lane.
Right. From your perspective, the other car looks like it's completely parked.
Exactly. But Einstein, who had been studying Maxwell's equations, realized that a frozen wave of light is mathematically impossible.
Wait, why?
The equations simply do not permit it to exist. A self-sustaining dance of electric and magnetic fields has to be moving at the speed of light to exist at all.
So it can't be frozen.
No! If it stops moving, the fields just collapse. There is no such thing as stationary light. So something was fundamentally wrong with the very concept of catching up to light.
That one question from a teenager basically shattered classical physics.
It really did.
But it took him a solid decade of turning it over in his mind to actually find the answer. Which brings us to the year that changed everything, the miracle year.
Ah, yes. The year is 1905. Einstein is 26 years old.
Okay, set the scene for us.
Well, he has no doctorate yet, he has no laboratory access, and the academic world has largely ignored him because of his rebellious, arrogant attitude as a university student.
Which is kind of funny to think about.
It is. He is working as a technical expert, third class, at a patent office in Bern, Switzerland.
He's sitting there examining blueprints for gravel sorters and electromechanical typewriters 6 days a week.
But he actually loves the patent office. He calls it his worldly cloister.
Because it was easy for him, right?
Yeah, examining patents was so easy for him, he could finish his day's work in a few hours, leaving the rest of his shift free to secretly scribble physics equations on scrap paper.
Which he would hide in a drawer when his boss walked by.
Exactly. And just as importantly, he had his best friend, Michel Besso, an engineer at the patent office,
They would walk home from work every single evening.
every evening, and Einstein would bounce his craziest, most radical ideas off him. Besso wasn't a physics genius, but he was a brilliant sounding board.
So he would poke holes in the arguments.
Yes, he'd listen, poke holes, and give Einstein the intellectual resistance he desperately needed.
So in just 1 year, 1905, while working a full-time job, Einstein publishes 4 scientific papers that essentially refound 4 entire branches of physics.
It's known as his annus mirabilis, his miracle year.
Just to give you an idea of how crazy this year was, in one paper, he definitively proved the physical existence of atoms by explaining Brownian motion.
Which is wild because before this, atoms were still heavily debated.
He showed that pollen grains jiggling randomly in water were actually being bombarded by invisible water molecules.
And in another paper, he explained the photoelectric effect, showing that light isn't just a continuous wave, it acts as discrete, chunky packets of energy, or quanta.
That paper is the foundation of quantum mechanics, and it's actually what won him the Nobel Prize decades later.
But the third paper published that year was the one that introduced special relativity.
And it is a masterpiece of logical deduction.
So let's break down special relativity for you. Einstein builds this entire earth-shattering theory on just 2 incredibly simple rules, or postulates.
Okay, rule number 1.
Rule number 1, the laws of physics are identical in all inertial reference frames.
Inertial reference frames. In simple terms, there is no preferred rest frame or stationary center of the universe, right?
Exactly. If you are moving at a constant speed in a straight line, like drifting in a spaceship with no windows, there is absolutely no physics experiment you can do to prove whether you are moving or standing still. The laws of physics work exactly the same.
Got it. And rule number 2.
Rule number 2. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer themselves.
So you cannot outrun light.
No, and you cannot slow it down by running away from it. Every observer in the universe will always measure light traveling at about 300 million meters per second.
It sounds incredibly simple, but think about what we just discussed with the train. If the speed of light is the same for everyone, no matter how fast they are moving, something else has to give.
Because you can't have a constant speed for 2 people moving at vastly different velocities unless the foundational variables that make up speed are altered.
Speed is just distance divided by time.
Exactly. If the speed number can't change, then distance and time themselves must change.
This is where we arrive at the first major reality-bending consequence of special relativity: time dilation.
Time dilation. Because the speed of light is absolute, time itself has to become flexible.
Okay, let's slow down and explain why time has to dilate. How does that mathematically happen? Let's do another thought experiment.
Okay, I love this one.
Imagine a very special kind of clock, a light clock. It consists of 2 parallel mirrors facing each other, with a single particle of light, a photon, bouncing straight up and down between them.
Every time the photon hits the bottom mirror, the clock ticks. Tick, tick, tick.
Now place that light clock on a glass-walled train, moving past you at incredible speed.
If you are a passenger on that train standing right next to the clock, you just see the photon bouncing straight up and down. Tick, tick, tick. Time feels perfectly normal to you.
But if you were standing on the platform watching the glass train zip by, the photon isn't just moving up and down.
Because the train is moving forward.
Right. The photon has to travel forward while it moves up and down. So from your perspective on the platform, the photon is tracing a long, diagonal zigzag path through the air.
Here is the crucial geometry. The diagonal zigzag path you see from the platform is physically a longer distance than the straight up and down path seen by the passenger.
But remember Einstein's second rule. The speed of light is completely constant for everyone.
The photon cannot speed up to cover that longer diagonal distance.
So if the light is traveling at the exact same speed, but it has to cover a longer diagonal distance from the platform watcher's perspective, then each tick of the clock must take longer to happen.
The clock on the moving train is literally ticking slower compared to a clock on the platform.
Time itself is passing more slowly for the moving object. Not because the mechanical clock is broken, but because the actual flow of time has stretched.
It's astonishing.
It really is.
Then at our everyday speeds, walking to the store, driving a car, the effect is so incredible microscopic we never notice it. It's billionths of a second.
But as you get closer to the speed of light, it becomes dramatic. The sources give a fantastic, concrete example of this happening in nature every single day.
Right, cosmic ray muons.
Yes, this brings it out of the realm of theory and into hard physical proof. Muons are subatomic particles. They are created when cosmic rays from deep space smash into atoms in the upper atmosphere, about 15 kilometers above the Earth's surface.
And a muon is highly unstable. It has an incredibly short lifespan. It decays and vanishes in just 2.2 microseconds.
Even traveling at 99.9% the speed of light,
Oh,
a muon should only be able to physically travel about 600 meters before its 2.2 microseconds run out and it ceases to exist.
But they're created 15 kilometers up. That is 25 times further than their lifespan should allow them to travel.
Based on classical physics, they should decay high up in the clouds. They should never, ever reach the ground.
But our scientific detectors on the ground are absolutely flooded with them. They hit us all the time.
How is that possible?
It is pure time dilation. From our perspective, standing stationary on Earth, the muon is moving at nearly the speed of light. Because it is moving so fast relative to us, its internal clock ticks incredibly slowly.
So to us, the muon survives the 15-kilometer journey because its 2.2 microseconds have been stretched out into a much longer period of Earth time.
Exactly.
But wait, let's flip perspectives. Let's look at it from the muon's point of view.
Okay, switching frames of reference.
To the muon, it's stationary. It's
Yeah.
just sitting there, and the giant planet Earth is rushing up toward it at 99.9% the speed of light.
In the muon's frame of reference, its internal clock feels perfectly normal. It only lives for 2.2 microseconds.
So how does it survive the trip from its own perspective?
That brings in the second consequence of special relativity, length contraction.
And its contraction.
Just as time stretches, space compresses. Moving objects, or space itself when moving relative to an observer, contract along the direction of motion.
So from the muon stationary point of view, the Earth is rushing upward at near light speed.
Because the Earth is moving so fast, the physical distance of the atmosphere contracts. To the muon, that 15-kilometer thickness physically shrinks down to just about 520 meters.
Oh, wow. So the muon easily crosses that radically shortened distance in its normal 2.2 microsecond lifespan.
Both perspectives are completely 100% physically correct.
To us, the muon's time slowed down. To the muon, the Earth's space squished.
It is the exact same physical event seen from two different inertial frames. Space and time are just warping and trading places to ensure the speed of light remains constant.
And this leads to a third consequence, which profoundly alters how we understand cause and effect, the relativity of simultaneity.
This one really messes with your head.
Let's use Einstein's train and lightning thought experiment.
Another train.
Picture a long train moving incredibly fast down a straight track. You are standing perfectly still on the platform. Just as the exact center of the train passes you, two bolts of lightning strike the train. One hits the very front engine, one hits the very back caboose.
And you are standing exactly halfway between the two strikes.
Right. To you on the platform, the light flashes from both lightning strikes travel the exact same distance to reach your eyes, and they hit your eyes at the exact same moment.
So you declare with absolute certainty those strikes were perfectly simultaneous.
But consider a passenger standing inside the exact center of that moving train.
Right, during the tiny fraction of a second it takes the light from the lightning strikes to travel through the air to reach them, the train has physically moved forward.
The passenger is moving toward the light coming from the front strike, and they are moving away from the light coming from the rear strike.
And remember, the speed of light is constant. It doesn't speed up or slow down for the passenger.
So because the passenger is moving toward the front light wave, that light hits their eyes slightly earlier. The light from the rear has to chase them, so it hits their eyes slightly later.
Which means the passenger declares with absolute certainty the lightning hit the front of the train first, and then it hit the back.
So who is objectively right? Are the strikes simultaneous, or did one happen before the other?
Well, Einstein's answer is they both are. Absolute simultaneity does not exist in our universe.
That's crazy to think about.
The ordering of events in time depends entirely on the observer's frame of reference. The concept of a universal, now across the whole cosmos, is a persistent illusion.
It fundamentally changes what it means to exist. And that brings us to the fourth consequence, from his 1905 papers.
Which culminated in a short follow-up paper containing arguably the most famous mathematical equation in human history.
E equals mc squared.
Energy equals mass times the speed of light squared. Einstein proved that mass and energy are not two separate things. They are two faces of the exact same coin.
Mass is just super concentrated energy.
And the c squared part is the conversion factor. Because the speed of light is a massive number, 300 million when you square it, you get a mind-bogglingly huge multiplier.
Like a 9 with 16 zeros after it.
Exactly. To put that in perspective for you, if you take just 1 single gram of matter, about the mass of a small paperclip, and completely convert its mass into pure energy, it would release the equivalent of about 21 kilotons of TNT.
That is comparable to the destructive yield of the atomic bomb dropped on Hiroshima, locked inside a single paperclip.
It is the underlying engine of the stars. It is why the sun shines. Deep in its core, 4 million tons of the sun's physical mass are being crushed and converted into pure, radiant energy every single second.
The 1905 miracle year changed the course of human history. But as incredible as special relativity was, it had a massive, glaring limitation.
Yeah, the word special means it only applies to special cases. Objects moving at a constant velocity in straight lines.
It completely ignored acceleration.
If a train sped up or turned a corner, the math didn't apply. And worse, it completely ignored gravity.
And gravity is the most important force in the cosmos. It holds you to the floor, it keeps the Earth orbiting the sun, it forms galaxies.
Einstein knew this massive gap existed, and it bothered him deeply. He needed a way to bring acceleration and gravity into the fold.
It took him 2 years of obsessing over it to find the thread that would pull the rest of the universe into his theory.
Which brings us to 1907. Einstein is still working at the patent office in Bern. He is sitting at his desk, staring into space, when he gets struck by an idea.
He later described it as the happiest thought of my life.
It sounds a bit morbid, but conceptually, it's brilliant. He imagined a person falling freely from the roof of a tall building.
While falling, for that brief, terrifying window of free fall, that person does not feel their own weight.
If they reach into their pocket, pull out an apple, and let go of it, the apple doesn't fall to their feet. It just hovers right beside them, falling toward the ground at the exact same rate they are.
For that brief duration in their local frame of reference, it is as though gravity has completely vanished.
Our sources use a fantastic visualization to really nail this down for you, and it's called the dual elevator thought experiment.
Okay, let's put you, the listener, inside a completely sealed windowless elevator car. You can't see, hear, or interact with the outside universe at all.
Scenario 1. This sealed elevator is floating in the deep void of space, far away from any planets, stars, or gravitational fields. You are floating weightless inside.
Suddenly, a cable attached to the top of the elevator pulls it upwards, accelerating the box at exactly 9.8 meters per second squared.
What happens inside? The floor of the elevator rushes up and pushes against the soles of your feet. If you let go of an apple, the floor rushes up to meet it, making it look exactly like the apple is falling at 9.8 meters per second squared.
To you, inside the box, this acceleration feels identical to gravity.
Now, scenario 2. We take that exact same sealed elevator, we bring it back to Earth, and we just rest it stationary on the ground.
Earth gravity pulls you and the apple down at 9.8 meters per second squared. You feel your weight pressing into your feet. You drop the apple, it accelerates to the floor.
Einstein realized something profound here. There is absolutely no local physics experiment you can perform inside that sealed room, no matter how advanced your technology, that can tell you whether you are accelerating upward in deep space or sitting completely still in a gravitational field on a planet.
They are locally indistinguishable. This became known as the equivalence principle.
Gravity and acceleration are fundamentally the exact same thing.
Okay, wait. I am going to push back here, because I want to make sure I am tracing this logic to its absolute extreme.
Sure, go ahead.
Let's go back to the first scenario. The accelerating elevator in deep space. Let's say I take a laser pointer and shine it perfectly horizontally across the room, from the left wall to the right wall.
Okay, so light traveling across the accelerating box.
It takes a tiny, tiny fraction of a second for the light to cross the room. But because the elevator is accelerating upward during that microscopic fraction of a second, the right wall moves up slightly before the laser beam hits it. So, to me, inside the elevator, the beam of light wouldn't hit exactly straight across. It would hit slightly lower. The beam of light would look like it's curving downward toward the floor.
That is exactly the massive, terrifying leap Einstein made.
But If you just told me that acceleration and gravity are the exact same thing and light curves in an accelerating room, does that mean gravity bends light?
Yes. Because of the equivalence principle, if a light beam curves downward in an accelerating frame, it must also curve downward in a gravitational field. Gravity bends the path of light.
But light has no mass. How can gravity pull on something with no mass?
That was the ultimate question. Realizing that gravity alters the path of light and the flow of time intuitively is one thing, but creating the mathematical framework to actually prove it, to calculate exactly how it happens.
That couldn't have been easy.
It took Einstein 8 agonizing years, pushing him to the absolute brink of his intellectual endurance and ruining his health in the process.
Because up until now, we picture Einstein as this lone genius who just naturally spoke the language of the universe. But the sources highlight the deeply human struggle of this period.
Einstein was incredibly creative, but he was not a master of advanced, cutting-edge mathematics.
Back when he was a university student, he skipped math lectures, calling higher math a luxury that a physicist didn't really need.
Now, his arrogance had caught up with him. He desperately needed a mathematical toolkit capable of describing a curved, four-dimensional reality.
So he had to swallow his pride and turn to his old college friend, Marcel Grossman, who'd gone on to become a brilliant mathematics professor.
Grossman introduced Einstein to a niche field called Riemannian geometry and tensor calculus. This was mathematics developed in the 19th century specifically to describe curved, non-Euclidean surfaces.
Just to clarify for you, Euclidean geometry is the flat geometry you learn in high school. If you draw a triangle on a flat piece of paper, the three inside angles always add up to exactly 180 degrees.
But if you draw a triangle on the surface of a globe, say, starting at the North Pole, going down to the equator, across the equator, and back up, those angles add up to more than 180 degrees.
That is non-Euclidean geometry. The rules change when the surface is curved.
And Einstein had to learn how to apply those rules not just to a 2D surface like a globe, but to a 4D fabric of space-time. He later admitted that he had underestimated mathematics his whole life, and that learning tensor calculus was the hardest, most punishing intellectual work he ever undertook.
But the result of that 8-year mathematical nightmare is the core thesis of general relativity. And if you take absolutely nothing else away from this deep dive, it should be this sentence.
Gravity is not a force.
It is not an invisible rope or magnetic tractor beam pulling you down to the ground. Gravity is the geometric curvature of a four-dimensional fabric called space-time.
The most common analogy used to visualize this, you've probably seen it in science documentaries, is a stretched rubber sheet or a trampoline.
Imagine a perfectly flat trampoline representing empty space-time. If you take a small glass marble and roll it across the trampoline, the marble travels in a perfectly straight line.
But if you put a heavy bowling ball in the middle, it creates a dip.
Okay, I have seen the bowling ball on a trampoline thing a million times,
Yeah.
but honestly, it has always bugged me.
Why is that?
Let's play it out. You put a heavy bowling ball in the middle of the trampoline. It creates a deep dip, curving the fabric. You roll the marble, and instead of going straight, it curves inward toward the bowling ball, maybe even orbiting it.
Right, and they say, look, that's gravity.
But wait, why does the bowling ball sink into the trampoline in the first place? Because the Earth's gravity is pulling it down. You are using gravity to explain gravity, and space doesn't have it down. So how does this actually work?
That is a brilliant observation, and you are completely right. The 2D trampoline is a fundamentally flawed analogy, precisely because it relies on external gravity to create the dent, and it only visualizes 2 dimensions.
So what's a better way to picture it?
To truly picture general relativity, you have to upgrade your mental model. Instead of a flat sheet, imagine a 3D grid of space, like a giant cube made of squishy foam or a 3D sponge.
Okay, I'm picturing a massive 3D grid.
When you place a massive object like the Earth inside that 3D grid, it doesn't sink down. Instead, the mass of the Earth pulls the grid lines inward toward its center from all directions. It concentrates and compresses the actual geometry of space around it.
So space is denser or more curved the closer you get to the mass.
Exactly. Now, in general relativity, objects moving through space always want to follow the straightest possible path. This straightest path through space-time is called a geodesic.
In flat, empty space, a geodesic is just a normal straight line.
But when the grid itself is warped and curved by a massive object, the straightest possible path curves inward toward the mass.
So when the Earth orbits the Sun, the Earth isn't being tethered or pulled by an invisible force. The Earth is just blindly rolling straight ahead, but the spatial grid around the Sun is so severely warped that Earth's straight path becomes a permanent circle.
Precisely. You are just coasting along the curved contours of space-time geometry.
Okay, but bring it down to my level. If gravity isn't pulling me down, why do my feet hurt when I stand up for too long? What is pushing me against the ground right now?
This is where it completely flips your perception of reality. You feel weight because you are being violently prevented from following your natural geodesic.
Really?
Yeah, the mass of the Earth radically curves the space-time you were sitting in, and your natural, unhindered path is to free fall straight toward the center of the Earth.
But the solid ground, the concrete floor beneath me, is physically in the way.
Right. The electromagnetic forces binding the atoms of the concrete floor together are physically pushing up against the soles of your feet, stopping you from falling.
So what I experience as weight or gravity pulling me down is actually the floor accelerating me upward, deviating me from my natural free fall path.
You are constantly accelerating upward against the curve of space-time just by standing still.
That is incredible. I'm not being pulled down. The planet is pushing me up. I love the quote from the legendary physicist John Archibald Wheeler that perfectly summarizes this incredibly complex symbiotic relationship.
Oh, it's the best quote.
He said, "Space-time tells matter how to move, and matter tells space-time how to curve."
It is the perfect distillation of the theory. The mass curves the map, and the map dictates where the mass goes. But of course, a beautiful mathematical theory is just pure philosophy unless you can physically prove it.
Which brings us to the proofs. It is 1915. Einstein finally has his complete equations, but he needs to test them against reality.
And the absolute perfect test subject was already hanging in the sky, frustrating the hell out of astronomers for decades. The planet Mercury.
Mercury is the closest planet to the Sun, sitting in the deepest part of the Sun's gravitational well.
It has a highly elliptical orbit, and its perihelion, the point where it swings closest to the Sun, gradually shifts or precesses around the Sun over time.
Like drawing a flower petal shape over centuries.
Exactly. Newtonian physics could explain almost all of this wobble by factoring in the slight gravitational tugs of Venus, Earth, and Jupiter, but it couldn't explain all of it.
There was a tiny, incredibly stubborn discrepancy of exactly 43 arcseconds per century that Newton's equations just couldn't account for.
And physicists were so desperate to save Newton that they literally invented a ghost planet.
They hypothesized there must be an invisible planet orbiting closer than Mercury, which they confidently named Vulcan, whose gravity was tugging on Mercury to cause the wobble.
But Einstein takes his brand new, insanely complex general relativity equations. He calculates the exact geometric curvature of space-time created by the massive sun, and he mathematically plots Mercury's geodesic path through that deeply curved space.
And without adding any invisible planets, without fudging any numbers, the pure geometry of curved spacetime spits out an extra precession of exactly 42.98 arcseconds.
A virtually perfect match. When Einstein saw that final number emerge from his calculations, he later told a friend his heart pounded so violently he thought something was physically wrong with him.
He was beside himself with joyous excitement. He knew in his bones that he had uncovered the true machinery of the universe.
But calculating the orbit of a planet we already knew about is one thing. To truly convince a skeptical global scientific community, the theory had to predict something entirely new, something that had never been seen before, and that could be independently measured.
It had to prove the craziest part of the theory, that gravity bends starlight.
Which brings us to the dramatic 1919 solar eclipse. Einstein's math predicted that light from distant stars grazing the edge of the massive sun should be physically deflected by the curved space.
He calculated the deflection would be 1.74 arcseconds, which was exactly twice the amount of deflection you would expect if you treated light as a particle with mass under Newtonian gravity.
The problem is you can't normally see stars right next to the sun because the sun is blindingly bright. You need a total solar eclipse to block out the glare.
This is where the human element, the sociology of science, really shines. The expedition to test this was led by Arthur Eddington, a prominent British astronomer.
You have to remember the context. This is taking place in 1919, just months after the horrific slaughter of World War I ended. Eddington is a Quaker and a deeply committed pacifist.
He had narrowly avoided being thrown in a British prison as a conscientious objector during the war.
So you have a British scientist risking his life traveling to the remote tropical island of Principe off the coast of Africa, battling mosquitoes and disease, all to prove the theory of a German scientist right after their respective countries had spent 4 years slaughtering each other in the trenches.
It's this incredible, beautiful act of international scientific solidarity bridging the wounds of war.
On the actual day of the eclipse, disaster almost struck. There was a torrential downpour. Heavy clouds completely covered the sky.
But just as the moon slid completely over the sun during the brief window of totality, the clouds thinned just enough for Eddington to expose a few photographic plates.
He managed to capture the faint light of the Hyades star cluster passing right near the eclipsed sun.
They packed up the plates, sailed back to England, and spent months painstakingly measuring the dots of starlight under microscopes.
And when they compared the positions of those stars to where they normally sit in the night sky, the stars had shifted.
They measured a deflection of 1.61 to 1.98 arc seconds, perfectly bracketing Einstein's prediction, and totally, provably incompatible with Newton.
When Eddington announced the results to a packed room at the Royal Society in London, it was like a bomb going off. The news hit the front pages of papers worldwide. Albert Einstein went to sleep a respected academic and woke up a global, household name superstar.
The 1919 eclipse is a spectacular historical story, but I want to connect this to your life right now. General relativity isn't just a historical curiosity. It is actively working in your pocket this very second.
Yes, let's talk about the GPS in your smartphone.
The Global Positioning System relies on a network of 24 satellites orbiting the Earth. Each of those satellites carries an incredibly precise atomic clock.
Your phone calculates your exact location on Earth by timing how long it takes for the radio signals from multiple satellites to reach you.
But those clocks in space are subjected to a massive relativistic tug-of-war.
Right, because of both theories we just learned about. Let's do the math. First, special relativity. The satellites are moving incredibly fast relative to the ground zipping around the Earth at about 14,000 kilometers per hour.
Because they are moving so fast, their clocks undergo time dilation. Their time ticks slower than ours. Because of their speed, they lose about 7 microseconds every day.
But then you have general relativity. The satellites are orbiting 20,000 kilometers above the surface of the Earth. Up there, they are much further away from the dense mass of the Earth, which means the curvature of space-time is shallower, the gravity is weaker.
And because they are in weaker gravity, time runs faster for them compared to the deep gravitational well on the surface. Because of general relativity, their clocks tick faster than ours by about 45 microseconds a day.
So you have conflicting forces. Minus 7 microseconds from speed, plus 45 microseconds from gravity. You get a net difference. The satellite clocks are gaining exactly 38 microseconds every single day relative to clocks on the ground.
Now, 38 microseconds sounds like absolutely nothing. But radio signals travel at the speed of light. In just 38 microseconds, light travels about 11 kilometers.
If the engineers hadn't believed Einstein, if they hadn't programmed the GPS satellites to deliberately slow down their clock's ticking frequencies before launch, to manually compensate for both special and general relativity, the entire GPS system would accumulate a navigational error of 10 to 11 kilometers every single day.
Within minutes of turning it on, Google Maps would be utterly, completely useless. It would tell you to turn left into a river.
So every time your phone accurately routes you around traffic or helps you find a coffee shop, Einstein's beautifully complex equations are silently chugging away in the background, measuring the exact curvature of space-time and the dilation of time to keep you on the road.
General relativity handles planets, satellites, and apples beautifully. But physicists are never satisfied. They always want to push the boundaries. What happens when you push this beautiful, elegant math to the absolute extreme? What happens when a massive star collapses in on itself and gravity goes to infinity?
We are entering the realm of extreme space-time, black holes and wormholes. And incredibly, the mathematical story of black holes actually starts right back in the horrific trenches of World War I.
Well, Einstein was relatively safe in Berlin. A brilliant German physicist and astronomer named Karl Schwarzschild was serving as an artillery lieutenant on the Russian front.
Between calculating artillery trajectories, Schwarzschild gets his hands on Einstein's newly published general relativity equations. And while sitting in the freezing mud, suffering from a horrific, agonizing autoimmune skin disease called pemphigus, which would tragically kill him just months later, he manages to do what Einstein hadn't even done yet.
He calculates the first exact mathematical solution to Einstein's equations. He maps out the precise space-time geometry around a perfectly spherical, non-rotating mass.
He mails his paper to Einstein from the trenches, and Schwarzschild's math revealed something deeply disturbing hiding inside the equations.
It showed that if you take any mass and you compress it down into a small enough radius, a threshold now known as the Schwarzschild radius, the curvature of space-time becomes infinitely steep. The dent in the 3D grid becomes a bottomless pit.
The escape velocity required to climb out of that gravitational well exceeds the speed of light.
And since nothing in the universe can travel faster than the speed of light, that means nothing, not even light itself, can escape. The ultimate trapdoor in the universe.
Einstein hated this idea. He genuinely didn't believe they could physically exist in reality. He thought nature would somehow intervene, that atomic forces would find a way to stop matter from collapsing that far.
It actually wasn't until 1967 that John Archibald Wheeler the Space-Time tells matter how to move. Guy finally coined the catchy term black hole.
To understand the anatomy of a black hole, you need to understand its two primary features. The first is the event horizon. This is the boundary, the absolute point of no return.
It isn't a physical, solid surface you could touch. It is simply the invisible mathematical threshold where the geometry of space-time becomes so warped that all possible directional paths point inward.
It's like a waterfall. Once you row your boat past the edge, you can paddle backward as hard as you want, but the water is moving down faster than you can paddle up.
Once you cross the event horizon, space and time effectively switch roles. Falling toward the center isn't just a direction in space anymore. It becomes your inevitable, inescapable future. You can no more avoid the center than you can avoid tomorrow.
And that center is the second feature, the singularity. This is where all the mass of the collapsed star has been crushed into an infinitely small, infinitely dense point.
At the singularity, the curvature of space-time is infinite, and all of our known laws of physics just completely break down. The math spits out division by zero. The equations throw their hands in the air and give up.
But what if a black hole isn't just a dead end? What if the bottomless pit goes somewhere?
This brings us to one of the most fascinating theoretical extensions of relativity: wormholes. In 1935, Einstein and his assistant Nathan Rosen were playing with the math of black holes, and they proposed that the singularity at the heart of a black hole might not be a crushed point, but a bridge.
A geometric tunnel connecting two different distant regions of space-time, or perhaps even connecting two entirely different universes. These Einstein-Rosen bridges are what we now casually call wormholes.
We see them in science fiction movies all the time,
Yeah.
but the media often misrepresents them. Based on our sources, specifically diving into the virtual reality simulation notes from astrophysicist Scott Manley, what would a wormhole actually look like if you flew a spaceship right up to one?
Right, because in the movies, it's always a flat, 2D, glowing circular doorway that you just fly through. But space isn't flat. Because space-time has three spatial dimensions, a hole in it wouldn't be a 2D circle. A wormhole would manifest as a 3D sphere.
Imagine approaching a planet. You see a perfect sphere floating in the darkness of space. But instead of seeing rock or swirling clouds on the surface of that sphere, the surface is a literal portal. You are looking at a sphere that is displaying the completely different star field and galaxies from the other side of the universe.
Manley's simulation notes describe the visual distortion beautifully. Because of the intense spatial lensing, where the fabric of space is so tightly warped around the mouth of the wormhole that light loops around it multiple times before escaping, if you orbit this spherical wormhole in your ship, the textures and stars on the surface appear to move backward relative to your motion.
And if you bravely cross the threshold, entering the mouth and traveling down the throat of the wormhole, the light gets completely mind-bending. Because the space is curving around you, you could look to your left and right, and the visual distortion would make it look like you are sandwiched between two flat, parallel, infinite planes of existence, even though you just flew into a sphere.
It's an absolutely stunning visualization. But before you pack your bags for the Andromeda Galaxy, there is a massive, seemingly insurmountable catch to wormholes.
While they exist beautifully as mathematical solutions on a chalkboard, making one that you could actually travel through without dying a traversable wormhole, known in physics as a Morris-Thorne wormhole, requires something that breaks our understanding of reality.
It requires exotic matter. Because gravity is an attractive force, the massive gravity of a wormhole desperately wants to crush its own throat, close the instant it forms. It pinches off before even a single photon could cross the bridge.
To prop the throat open so a spaceship could safely fly through, you need to counteract that crushing gravity. You need something with a repulsive gravitational effect. You need exotic matter with negative mass.
Negative mass. To be clear, we are not talking about antimatter. Antimatter has normal mass. We are talking about something that literally weighs less than nothing.
An apple with a mass of -1 kilogram, if you push it forward with your hand, the physics dictates it would accelerate backward into your hand.
And here is why this is a massive problem for everything we've talked about today. Negative mass fundamentally breaks Einstein's equivalence principle.
The equivalence principle assumes that your inertial mass, how hard it is to push you, and your passive gravitational mass, how much gravity pulls on you, are identical. All experimental evidence in human history says they are the same thing. Negative mass would shatter that foundation.
So while wormholes are incredibly fun to visualize and mathematically possible on paper, without exotic matter, they remain heavily locked in the realm of hypothetical math.
Okay, so general relativity is incredibly successful. It predicts the orbital mechanics of planets, it predicts black holes, it makes the GPS in your phone work. But Einstein's journey wasn't entirely a victory lap.
Which brings us to the final act, Part 7, the unfinished symphony. The things Einstein got spectacularly wrong and the final boss of physics that still haunts scientists today.
In 1917, Einstein was feeling ambitious. He tried to apply his beautiful, proven equations to the entire universe as a whole. But when he crunched the numbers, the math told him something he flatly refused to believe.
The equations dictated that the universe could not be static. The mutual gravitational attraction of all the mass in the universe should cause all the galaxies to eventually collapse in on themselves, or, alternatively, the universe must be actively expanding outward.
But you have to remember the scientific consensus of the time.
Mhm.
In 1917, absolutely everyone believed the universe was static, eternal, and unchanging. They thought the Milky Way galaxy was the entire universe.
So Einstein, trying to force his elegant math to match the accepted reality of the time, awkwardly duct-taped a new variable into his equations. He called it the cosmological
It
constant.
was basically an arbitrary repulsive pressure he inserted, just to perfectly balance out the crush of gravity and keep the universe sitting completely still.
It was a mathematical fudge factor. He didn't have a physical explanation for it, and he knew it was deeply inelegant. Then, in 1929, the American astronomer Edwin Hubble pointed his massive telescope at the sky and studied those fuzzy patches of light they called nebulae.
Hubble proved that they weren't just gas clouds. They were entirely different, distant galaxies. And more importantly, by looking at the redshift of their light, he proved they were all hurtling away from us.
The universe was expanding. Einstein's original math was right all along. Einstein visited Hubble, looked through the telescope, and supposedly called the insertion of the cosmological constant the biggest blunder of my life. He threw the variable in the trash.
But the universe has a massive, beautiful sense of irony. Jump forward to 1998. Teams of astrophysicists are measuring the light from incredibly distant supernovas. They expect to see the expansion of the universe slowing down over time, exhausted by the inward pull of gravity.
Instead, they find the exact opposite. The expansion of the universe isn't slowing down, it's speeding up. Something invisible is pushing the fabric of the universe apart at an accelerating rate.
They call this mysterious repulsive force dark energy. And here is the kicker. Mathematically, dark energy behaves exactly like Einstein's discarded cosmological constant.
The very patch he called his biggest blunder, the duct tape he threw away in shame, turned out to be a fundamental, dominant reality of nature, making up roughly 68% of the total energy density of the cosmos. He was right, even when he thought he was wrong.
But there's one war Einstein fought that he absolutely lost. The war with quantum mechanics.
This is the ultimate final boss of physics.
General relativity is an undisputed masterpiece of the macro universe. It perfectly describes a smooth, continuous, deterministic fabric of space-time. Planets followed predictable geodesics.
But in the 1920s, the quantum revolution exploded. Quantum mechanics was developed to describe the subatomic realm, the world of electrons, photons, and quarks. And that microscopic realm is not smooth or deterministic. It is chunky, jittery, chaotic, and entirely probabilistic.
Particles don't have exact locations. They exist in smeared-out clouds of probability until someone measures them.
Einstein hated this with a passion. He famously complained, "God does not play dice with the universe." He deeply believed in local realism, the idea that objects have definite, concrete properties, whether you are looking at them or not. The moon is still there, even if you close your eyes.
But decades of quantum experiments have definitively proven Einstein wrong. The quantum world is intrinsically probabilistic. The dice are real.
But the real tragedy, the crisis that haunts physics to this day, is that these two incredibly successful theories, general relativity and quantum mechanics, are mathematically incompatible. They refuse to talk to each other.
Let me guess, if you try to combine the math, it breaks.
Exactly. If you try to use quantum equations to understand the smooth geometry of general relativity, or if you use relativity to map the jittery quantum world, the math completely breaks down. It spits out infinities and nonsense probabilities. They cannot both be fundamentally true at the same time, and there is nowhere this violent clash is more obvious than at the edge of a black hole.
Which leads us to the information paradox. In the 1970s, Stephen Hawking was combining the two theories just at the event horizon of a black hole. He realized that because of chaotic quantum fluctuations, particles popping into and out of existence, black holes aren't entirely black.
They slowly leak a tiny amount of thermal energy, which we now call Hawking radiation. And because they are leaking energy over unthinkably long stretches of time, trillions of years, they will slowly shrink and eventually completely evaporate into nothing.
But here is the massive problem. Quantum mechanics is built on a foundational, unbreakable rule. Information cannot be destroyed. The exact quantum state of every particle in the universe must be preserved, allowing you, in theory, to rewind the clock and see the past.
So if I throw a massive encyclopedia into a black hole, the black hole swallows the mass and the unique quantum information of that book.
Right. General relativity says nothing escapes the event horizon. The encyclopedia is trapped, but then, over trillions of years, the black hole evaporates via Hawking radiation.
And what happens to the encyclopedia?
That's the paradox. Hawking radiation is completely random thermal noise. It carries no information. The radiation looks exactly the same whether the black hole swallowed a dead star, an encyclopedia, or a grand piano. So when the black hole finally vanishes completely, where did the unique quantum information of that encyclopedia go?
If the information is truly deleted from the universe, it completely breaks the foundational laws of quantum mechanics. If the information somehow magically escapes the event horizon, it completely breaks general relativity. It is a terrifying paradox that forces us to admit we are missing something huge. The brightest minds in the world are still trying to solve it today.
It is the ultimate cliffhanger in physics. It is a humbling reminder that our understanding of reality, while profound, while capable of predicting gravitational waves over a billion light years away, is still incomplete. There is another revolution waiting to happen.
And that brings us to the end of our deep dive. Let's recap this incredible journey we've been on. We started with 4-year-old boys staring at a trembling compass needle, realizing invisible forces rule the world.
We saw how a teenager's simple question about running next to a light beam eventually broke the universe, forcing us to accept that the time itself slows down to keep the speed of light constant, saving the short life of a falling atmospheric muon.
We learned that dropping an apple in an accelerating elevator proves that gravity isn't a tractor beam pulling you down. It is the invisible, curving geometric geography of the universe, dictating the straightest possible path for the Earth to roll around the sun.
We explored the terrifying math of black holes, visualized wormholes as crystal spheres, and realized our expanding universe is being pushed apart by Einstein's biggest blunder.
You are not floating in a static, empty void. You are intricately woven into a living, bending geometry. Every single breath you take, every movement you make, subtly shifts the curvature of the world around you.
Before we sign off, we want to leave you with a final, provocative thought. It's something we didn't explicitly cover in the main timeline today, but it is an inescapable philosophical conclusion of all this physics. We talked about how time slows down and simultaneity is relative. Because of this, in relativity, time isn't a flowing river that moves from past to future. Time is just a dimension. It was a fixed coordinate on a landscape, exactly like up, down, left, and right. As physicists call this concept the block universe. In the block universe, the past, the present, and the future all exist simultaneously in a massive, unchanging block of space-time.
Einstein actually found deep comfort in this. When his lifelong best friend Michel Bazio died, the guy he walked home with from the patent office, Einstein wrote a letter to Bezos' widow. He wrote, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. If gravity bends time, and time is just a flexible path you walk down like a road, is your conscious experience of right now just an illusion? Are all of your yesterdays and all of your tomorrows already written, permanently existing in the immutable geometry of the cosmos? And if a black hole really does delete quantum information at the end of time, does the universe eventually forget you ever existed at all?"
It is a beautiful, haunting perspective, something to mull over the next time you accidentally drop your keys on the floor. Remember, they aren't being pulled. You're just watching them freely follow the ancient invisible curves of reality. Thank you so much for joining us on this deep dive into the cosmos, but we'll see you next time.